Yeah, so I'll talk through the title from the start of the presentation. Maybe the first third will be explaining all the nonsense in the title. Yeah, this is joint work with the wonderful five authors, my now ex-supervisor Dmitry Shishkov, the guy I now work under, Wojciech Czerwiński, Łukasz Orlikowski, and Karol Bojanczycki, that went to Fox last October, I suppose. Yeah, so without further ado, I'll just introduce vector addition systems for those. I guess, is there maybe by a turn of hands who knows what a vector addition system is and is fairly familiar? Okay, there's enough not hand that I'll go through this. So I'll give you an example just to kind of keep it moving quite quickly. So here is a vector addition system with states. Specifically a two-dimensional one, so it consists of states that are connected by transitions that are labeled by two-dimensional vectors. And we'll shorten vector addition system states to VASS, otherwise I'll run out of time to talk to you. And I'll ask the question of reachability. So is there a run from a given initial configuration to a given final configuration? And the important detail for vector addition systems is that the counters must remain non-negative at all times. So to be precise, you'll start in this case at A with 0 and 0 on your two counters. Whenever you take a transition, you will update each counter by the components of the vectors respectively. So you do vector addition over and over and over again. So let's run through this instance. Sorry, there's no chair. From A, you'll start with 0, 0. Notice you can't, you're only two transitions up, to B or to C. You can't take the transition to C because you'll subtract 7 and you'll die immediately on the first counter. So you have to go down to B with counter value 2 and counter value 0. Then from B, you have to go to C and you'll reach 5, 8. Then you have to go to E and you'll reach 3, 10. Then you, just by choice, go down to D with sum 7, 5. And now notice that your goal is to get to G with counter values 4 and 5. And regardless of whether you go via F or not, you're certainly going to go negative on, well, either counter. So you have to do something. If you stare for a while, you'll notice that there's a cycle back here that you can take that will increment your first counter by 1 and your second counter by 10. So we'll take that twice, and now, rather conveniently, you can take the transition directly to G to get you to 4, 5. I don't know if anyone spotted the solution to this instance. They probably guessed it was a positive instance based on the framing of how I was introducing it, but like spotting the path is really difficult. And this is just a two-dimensional system, right? So it's just to demonstrate the difficulty involved in solving reachability. It's probably no surprise to anyone, but hopefully that's cleared up roughly what VASS is to be haven't seen VASS before. And I can ask the question more generally, right? Like I need not restrict myself to 2 dimensions. In fact, in this presentation, you'll see 3-dimensional systems and systems of high dimension beyond that. But the problem gets really bloody difficult really bloody quickly. So I'm going to make a restriction. And I put simple in the title, simple vector addition system states. What do I mean by simple? Specifically, I'm going to study flat VASS, a flat VASS. So there's a structure restriction on the states and transitions, whereby every state belongs to at most one cycle. Here's 2 VASS. I can remove all the labels because it's a structure restriction. One of them's flat, one of them's not. It takes you a moment to spot it. This guy's flat. There's a P, Q, R cycle, and there's an S cycle, but P, Q, and R only belong to one simple cycle, and S only belongs to one simple cycle. Yet the guy on the right is not flat, right? There's A, B, C, D, and C, D, F back to C. So C and D belong to 2 simple cycles. Very roughly speaking, flat forces you to not have nested loops of some description. So here you could go on a loop around here and then a loop around there and nest your cycles and overlay them one after another. Flat has a feeling of once you've done the PQR cycle and you leave, you're never going to come back to that cycle again. So there's kind of a DAG structure with cycles that are disjoint from one another. And so paths through flat VASS are inherently simpler in some way, and that is reflected by how complex the reachability problem is in flat VASS. At any point, like, please interrupt me if you're confused with what's flat or anything. Just say, I don't understand. It's kind of the point of being here, right, to understand something. So please do interrupt. Anyway, the first, and this is kind of going to set the scene, because this was the tractability border for a certain reachability problem. All problems here are in NP. So what do I mean by that? Regardless of the dimension, so when I don't specify the dimension, and I'm allowed binary encoding, reachability is always in NP in flat VASS. This can be lifted from work from 97. It was only really written in this format in a more recent paper. The idea is not new. I'm not going to go through it, but you can write these things down in Presbo. It's not ridiculously difficult. And unfortunately, if you have binary encoding and just one counter, the problem's NP hard already. So if you're allowed binary encoding, reachability is NP complete, basically. As a warm-up, because we're going to see some other NP hard reductions, I'm going to show this off. First, we're going to reduce from subset sum with more simplicity. So I'm allowed to take each of the subset sum items as many times as I like. It's not just the 0-1 variant of subset sum. And I construct this flat VASS. It's flat for a very obvious reason. Q1 belongs to one simple cycle, Q2 belongs to one simple cycle, etc. And I ask the following reachability queries. So I'm going to ask from Q1 with counter value 0, can I reach Qn with counter value t? It's pretty straightforward. If all of the values x1 through xn are positive, then you don't need to worry about the counter going negative. Reachability is therefore NP hard. If there is a subset, if there is a solution to the instance of subset sum, it will tell you how many times to take each cycle, and vice versa. If reachability holds, you look at how many times you took each cycle, and that will tell you the solution to subset sum. Convincing? Question?
Yeah. Normally, subset sum is sort of just 0 one way. K can be 0. That changes how we change modify work that.
Yes, I can do that as well. Imagine, so if you force 0-1, you're saying, I can have a branch. So imagine, get rid of the loops. I'll have a branch between Q1 and Q2. There'll be 2 transitions, one that gives you +0, one that gives you +x1, etc. So yeah, that works too. I chose this on purpose for a reason that you will find out later. It's a bit cheeky.
Because unary plus one of us is a P.
Jumping the gun. You'll find out it's NL. I'm not going to show why, but we're going to study problems very close to that. Okay, that was the proof. That wasn't even just a proof sketch, really. And yeah, answering your question, reachability in flat VASS is in NL for 1- and 2-dimensional systems. For 1-dimensional systems, it's not particularly difficult to see. You can argue that there is a bound on the counter such that if you ever exceed that bound on the counter, you can depump and shorten a run. So in a minimal length run with saying reachability, the counter value will be bounded by a polynomial in the number of states in the one VASS. You can then draw out the graphical configuration. It's going to be maybe quadratic in size, and then you could just explore this in NL using d-VASS or something. Reachability in 2 VASS is not so obvious. I'm not going to talk about that. That's not my job. But what about beyond, right? So I've kind of justified here, binary encoding is quote unquote done, right? So we're only interested in unary systems, but it's NP hard for dimension 7, right? This is where it's immediately very curious. So reachability is hard for dimension 7. This is a fairly recent result. That was then improved to dimension 5, and then to dimension 4. So the burning question that you must all be raging to know is, what's the complexity of reachability in unary flat 3 VASS, right? It's the only case that remains, and that's the main purpose of this presentation, but not the only thing I'll be showing you. And it was asked by a couple of people, those are the citations. That's not a simple enough structure for me. I want to make my life more difficult. So I'm going to go from flat VASS down to linear path schemes. A linear path scheme is a kind of flat VASS where the structure is of the following form. There is a linear path underlying, and there are disjoint cycles connecting them. So in a sense, you're not allowed branching. Think of this kind of picture. There's a linear path underlying, you're allowed cycles that are disjoint in the flat sense. But in flat VASS, I was allowed branching behavior. Here I'm not, hence your question, or my answer to your question. I'm going to go even further. That's not simple enough. I'm going to go to what has been called simple linear path schemes, which is linear path schemes, but the loops have length at most 1. Like, this structure is hilariously simple at this point. There's kind of almost nothing you can do. You can go along, you can take updates along the transitions by force, right? Forced to go along the path, and you can choose how many times to take each cycle. That's all you can do. And there was a question asked a couple times, which is, in linear path schemes, forget even simple linear path schemes, is reachability hard? Is reachability easy? Specifically, I think they were interested in showing whether reachability in maybe linear path schemes or simple linear path schemes had a polynomial time algorithm for dimension 3. That was a question that was explicitly stated, but generally nothing was known. The previous slide where I said, oh, dimension 7 was hard, that was for unary systems, and they really used branching behaviors in these productions. We answered that question with the simplest form of these linear path schemes has NP hard reachability all the way down to dimension 3. So we kind of answer all the questions by saying, it's hard, unfortunately. And it requires some care to see how this works. I will go through the whole proof. This is, I think, the most interesting bit of the paper. Again, stop me at any point, it's going to slowly get more technical. So we're going to show it's NP complete. We already know it's an NP no matter how many counters, no matter the encoding, so that's fine. For the reduction, we're going to reduce from 3 SAT directly somehow. And we're going to use the Chinese remainder encoding for SAT. If you've not seen it before, it's going to be really cool. If you've seen it before, you get mad. And then I'm going to use the Chinese remainder encoding for SAT to turn SAT into a conjunction of non-divisibility assertions. This is quite nice, but it's not new in our paper. It's just represented. And then we design, curiously, a 2-dimensional system with some 0 tests, which sounds dangerous, but don't worry, I'll clear that up later, for asserting non-divisibility. And then we'll concatenate and get a massive system that simulates the conjunction of non-divisibility assertions, but has 0 tests. Then we'll get rid of the 0 tests and add a counter, and we'll get a 3-dimensional system. That was quite a lot of information. I will go through this one by one. This is next. So suppose I want to encode SAT as a conjunction of non-divisibility assertions. What gives? Let's have k variables in our SAT instance. And I will now imagine how to have the first k primes, p1 through pk, and I'm going to choose the following encoding. I'm going to find a natural number n such that n is congruent to 0 mod the ith prime, if only if I want xi to be false, and I'm congruent to 1 mod the ith prime, if only if I have xi is true. Notice that for, well, at least the second prime, 3, you could have an n that is equivalent to like 2 mod 3. That would encode not an assignment. So somehow it's critical to observe that n need not encode an assignment. So if I pick an n, I need to check whether it encodes an assignment before I can even check whether it encodes a satisfying assignment. So first, I want to enforce validity. I want to find an n that is that satisfies n is equivalent to 0 or 1 on pi for every I. One slide, one step ahead. So the crucial bit here is if I imagine later, this is kind of a disjunction, right? And I want to get a conjunction. So I'm going to complement this statement. So rather than checking that I'm equivalent to 0 mod pi or 1 mod pi, I'm going to check that I'm not equivalent to all of the other neighbors. So I'm going to check that I'm not equivalent to 2, not equivalent to 3, and not equivalent to 4, etc., all the way up to not equivalent to pi minus 1. And this is equivalent to non-divisibility assertions. Instead of checking that I'm not equivalent to 2 mod pi, I can say, oh, n minus 2 is not divisible by pi, and n minus 3 is not divisible by pi. Does that make sense? If this doesn't make sense, ask, please. This just enforces that if I chose an n that I'm guessing as a satisfying assignment, all this does is it doesn't check if it's satisfying, it just checks it's valid. It just forces that either I'm equivalent to 1 or 0 mod pi for all I, and now I need to check that I'm satisfying. And it's kind of roughly what one might think. Let's go for an example clause. Let's say x1 or not x2 or x3. So this is satisfied if if n is equivalent to 1 mod 2, right? Because this is the first prime, or 0 mod 3 or 1 mod 5, right? Instead, because I can't deal with these silly conjunctions, disjunctions, I want a conjunction. This will only be falsified when n is equivalent to 10 mod 2 times 3 times 5. To see why this is the case, you would need this to be falsified if n was equivalent to 0 mod 2 and 1 mod 3 and 0 mod 5. I can then compress this into one statement. And now I have a single non-divisibility assertion, because instead of testing whether n is equivalent to 10 mod 3, 2 times 2 times 5, I can check whether 2 times 2 times 5 does not define n minus 10. Does that make sense? Now, you stare at the slide, I just have a conjunction of non-divisibility assertions. I'm always saying something does not divide number, something does not divide number, something does not divide number, and they're all conjunct together. I will end up having something like number of variables squared plus number of clauses. So I get a polynomial number of queries. So now I have an instance of checking whether there exists an n that satisfies all of these non-divisibility assertions that will apply sat. Is that okay? Even if it's not okay, pretend it's okay, because we're going to continue. I continue. Oh, here we go. Okay, right. So this is definitely fine. And now you're gonna kind of have to follow me. I'm going to design a system that will only be that will test for non-divisibility, basically. And I will design a system with 0 tests because it's quite hard to design a system. Remember, we're aiming for a 3-dimensional system, so I'm going to have a 2-dimensional system with 0 tests, and then later I'm going to kill the 0 tests at the cost of an extra counter. Doing this all at once is very difficult and extremely opaque, so I'm going to go through it step by step. So maybe don't worry exactly about the design of the proof, but let's just worry about the system with 2 counters and 0 tests. I hopefully can continue. Okay, you can switch to pressing the key on the keyboard if you want. I might forget this. Okay, so suppose, for example, that we want to assert 7 does not divide some value v, right? So I'm going to have a counter. I'm going to have 2 counters. I'm going to have a counter with value v to start with, and some auxiliary counter that's going to help me do some checking. And then I would like this gadget, I'm going to draw it on the right-hand side of the slide in just a minute. And I would like you to only be able to pass through this gadget if 7 did not divide the original value v. And then I would like to come out of the end with x is equal to v again. So in theory, I could then test that 9 does not divide v, and I can conjunct these together. So I have a simple linear path scheme that tests non-divisibility, and then I'm going to restore the counter values so I can then have another path scheme do another test, etc., etc. So it's invariant after every copy of this gadget. Here it is. I'm going to talk through it, don't worry. It's fairly straightforward, but it's kind of it's doing subtle things. So I'm going to break it down into 3 parts. The first, so recall that we're going to 2 counters, x is the first, y is the second. Immediately you'll start with forcibly taking this transition. So you'll put 5 counter value onto y, and you'll have v plus 1 on x. And then you've got a cycle that allows you to move the 5 counter value from y to x however you like. So you can take a value, I don't know if you want x plus 1 or x plus 2 or x plus 3, all the way up to x plus 6. And you can load that value onto the x counter. So you'll end up with x plus r on, sorry, v plus r on the x counter, and then some remainder on the y counter that you need not worry about. And then in the second step, you're going to subtract multiples of 7. Right? You're going to subtract 7 away as many times as you like, and then you're going to 0 test the x counter. The idea being for x to be 0, right? So this transition only is fireable if x is 0. This transition, the 0 test one, is only fireable if there was a certain choice of r that got v plus r to be divisible by 7, right? And if there is a value between 1 and 6 such that v plus r is divisible by 7, then v could not have been, to start with, divisible by 7. Does that make sense? That's like the most important part of this gadget. It's pretty straightforward to then recount the counter value. So notice after this red segment, right, like where the line is cut, I'll have 0 on the x counter and something on the y counter, and I wanted to recover the invariant that I end where I start with the counter values. So I'm going to have to push them all back. So what I'll do is I'll just immediately take, well, let's actually identify what the value of y is. Notice that when you started, the counter value on x was v and y was 0. And these 2 loops preserve the counter value. Like adding and taking 1, the sum of the counter values doesn't change. Adding and taking 7 doesn't change the sum of the counter values. So the counter values after the first transition were v plus 1 and 5. That sums to v plus 6. Then those 2 cycles didn't change that value. So after this red segment, x will be 0 and y will be v plus 6. I'll then use this loop of the plus 1 minus 1 loop, and then a 0 test on y to shove all the value back to x. Then x will have value v plus 6. I will have value 0, and then I'll just subtract 6 away, and I'm left where I started. Okay. And now we're basically done. If I can now test non-divisibility, I can then conjunct these together one after another, and I can test with different values. I can test X is not divisible by 7, X is not divisible by 9. You choose what you want to test non-divisibility against. The one catch is, though, that if I go back for a moment, X was kind of the value counter. And if you remember the site reduction, I wanted to guess a value N such that non-divisibility conjunction holds. So if I just conjunct these together, that's not good enough. So I have to have at the very, 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 very start a little loop that allows you to set the value of X to be whatever you like. So a little loop that adds 1 to X. Yeah, to guess an assignment, and then you move on. And now, unfortunately, I don't have time, I don't think, to go through why this works, but I will just show you a lemma statement. There it is. Basically, there's this, it's very technical. I just thought I'd flash it on the screen for the sake of it. It's not original, but the modifications to preserve the structure of the linear path scheme is in here and was not in previous papers, but you can trace the lineage of the ideas back a couple of years. Basically, the point of this is if you input a VASS, I think here we called it Z, with a certain number of 0 tests. So it said that Z has the property of only accepting run. There are at most M 0 tests, so some small number. Notice if you go back to the, this will only have 2 0 tests. And I said that we're going to do one non-divisibility assertion for something like the number of variables squared plus the number of clauses. So it's going to be a polynomial number of 0 tests in total, which is relatively small. And so I just feed this in. I will get out a d plus 1 dimensional VASS, right? That's the key bit. So I'll feed in this case, a 2 VASS with 0 tests. I'll pull out a 3 VASS without 0 tests. Reachability is preserved. It can be constructed fairly quickly and it's not too big, blah, blah, blah. It's not that interesting. We'll use that as a black box. But the main takeaway message from this lemma is if you have a small number of 0 tests, which we do because they're on the skeleton underlying, right? There cannot really be that many down there. Then you can simulate those 0 tests with another counter. The reason I'm talking about this is because the ideas are not really involved. But I can talk about it. So if you want to know how to simulate these 0 tests, I will happily sit down and put you to sleep whilst talking on a whiteboard. No problem. Okay. No, we're done, which is great. So I think this roughly gives the main idea behind why reachability in unary, simple linear path schemes, is anything hard, and that's answering the questions I showed you earlier. Any questions before I move on to other bits? Yes.
You're dividing by relatively large number.
Not true. Right. Good question. Good observation. So these are the non-divisibility assertions. The kth prime is something like k log k. Here you're doing non-divisibility against up to the kth prime. Here you're doing non-divisibility up to a product of 3 primes, something like k cubed log k. So you're only ever doing, yeah, there's a subtle point. I purposely didn't mention it, but yeah, good question. This is poly. The value n doesn't matter, right? Because the loop of in example minus 7 it doesn't matter.
What do you do?
Is that convincing?
It's, yeah.
Okay, cool. Ish is good enough. Okay, right, we were here. So, any other questions? Other main results. I'm going to skim all of them with varying detail. I've got an optimistic aim to show some nice detail for the very final one. I'm being optimistic, so don't worry if it doesn't make any sense. We have these 3 theorems. So the first is what's going on, ultra flat for VASS, what's going on. Similar to the first theorem, I will define them in a minute. And then there's this unitary inverse Ackermann dimensional system. What's going on there? I'll show you that. I'm basically going to show you the statements and a very rough flavor for the proofs. They're very similar to what we did in theorem 1, but not entirely. And then we have an upper bound for not a 3-dimensional system, but some generalization of a 2-dimensional system. So if you're given a unary system, we saw earlier the reachability in unary flat VASS was in NL, rather it's in P is fine. But that assumed that the initial and final configurations were encoded also in unary. We generalized a little bit to allow for essentially large starting and large target configurations. And we still show that we're in P. We don't show NL, so it's not quite comparable. And we don't do it quite for flat, we do it for simple linear path schemes, but maybe it can be generalized to flat. Yeah, so I'll talk about that later, but next up, or the next up of 3 slides, I think it's maybe 4 slides. I'll show you definitions and just the basic ideas. So they're even simpler than linear path schemes, right? Like, it's not simple enough. I'm on a quest to find the simplest system. An ultra-flat VASS is a simple linear path scheme where the transitions between the self loops have no effect. So literally this system has zero effect all the way through. The only thing you can do is choose how many times you take each loop and take the effects from those loops. That's it. Here's the kind of like a modified example of the divisibility testing gadget from earlier. I killed off the zero tests just for the picture. This thing is not ultra flat because I'm updating. Oh, sorry, I should have said all of the unlabeled transitions have zero effect, but I labeled them. It's not ultra flat because I'm updating between samples. So if I just set them to be zero, this is ultra flat. It seems ridiculous to believe that reachability here could be hard, but it is. Oh, and also, this is a really nasty way of drawing these. So I'm just going to draw them as like little counter programs, nice and dense. Look how small the figure became. So I'll have an X counter, the first counter, Y counter, and I'll just write it like this. When I say loop, it's not exhaustive, it's just non-deterministic. I can take the loop as many times as I like and then move on to the next line of the program, just like in the VASS. And we show, firstly, yeah, coming back to what you were picking up on, reachability in binary ultra-flat, one VASS is already hard. So if I'm allowed binary encoding again, it's already hard. Oh, wait, it's the same proof. This is an ultra-flat VASS because I'm not updating between the states and I've got simple self-loops. It's in NL because already for flat VASS it was in NL. So then the question was really like, is ultra-flat VASS with unary encoding in P for any dimension at least 3? So basically the same question as earlier, asked by Leroux. And we showed no, but for dimension 4. So we basically modify what we did, simple linear path schemes, but we pay one counter cost for our applications. It's slightly frustrating. So we almost answered this question, but not quite. I'm not going to go any further than just giving you the soup of proof ingredients. Here is the soup. It is the same, basically the same soup as before. So I will just through that. I will give you the Chinese remainder encoding. There are the conjunction of non-divisibility assertions. And then the main difference is that instead, I will have an ultra-flat 3 VASS with 0 tests that can assert non-divisibility, and then I'll concatenate them together just before, and then I'll simulate them with, I'll simulate the final counter, I'll simulate the 0 test with the final 4th counter, and then I'll end up with a 4 VASS instead. I'm going to go no further because this gadget even looks really similar. I think, if I rendered it correctly, bonus slide if you really want to see it later. It's just slightly more nasty. But yeah, if you remember in the non-divisibility gadget for simple linear path schemes of dimension 2, I did that update at the start, +1, +5. I'm not allowed to do that anymore. So I do have to do something a bit smarter, but it's not wildly different. So that was the second theorem. The third was about unitary simple linear path schemes. What on earth is going on here? I wasn't done on my quest for a simple system. So I'm going to say that a unitary simple linear path scheme is in a VASS where the updates are restricted to really just be not even unary, but +1, 0, or -1. Normally that's the same thing as unary because you can have unknown update +5, be simulated by 5 +1s in a row. But because of the restriction of simple self loops, I'm not allowed to blow that up into 5 transitions. So if I take this example again, I can blow this up into 5 transitions, which is fine, but I can't do -7 +7, because if I terminate to 7 transitions, I lose the simple property. It's not a self loop anymore. So really, reachability here is also unbelievable that it can be hard. Our theorem is that we don't get a constant dimension for hardness. So we don't just pay one counter, we pay inverse Ackermann many counters for hardness. This seemingly doesn't make any sense, so let me just define the problem. And this was kind of a joke that I gave because at Foxhall, their problems have really long names and acronyms. So I thought I'd give an even longer name and even longer name for the problem of unitary inverse Ackermann dimensional linear path scheme reachability. The input first is, let's just write down some number in unary. And I will have a simple linear path scheme that has O alpha, where alpha is the inverse Ackermann function. So something like a constant time inverse Ackermann many counters, but the size, the length of this thing is allowed to be polynomial in this unary value k. So the system can be reasonably sized, but the number of counters is too small. Initial configuration encoded in unary, a final configuration encoded in unary, and its reachability, the same question, can I go from the initial configuration to the final configuration? Nothing special. I'm going to use soup again. So it's the same thing, but you really like, okay, now it's getting, the headache's getting really like thick. So we're going to have a 5-dimensional system that tests for a certain amount of visibility, and it has 0 tests. But the most annoying thing was that previous black box lemma that I gave you is really not unitary, like really, really not unitary. So we have to come up with a new idea for how to simulate 0 tests. That is where we pay the inverse Ackermann cost. To give a one-liner, we take normal VASS that can simulate Ackermann counters and flatten it out into a massive, effectively Ackermann-sized machine. And instead of having D counters in Ackermann-sized machine, we'll have inverse Ackermann many counters in a D-sized machine. Very roughly speaking. But I'll leave that there. I can talk at a later time. So I've reserved, I think, enough time, maybe too much time, so I apologize for taking so quick, for the final theorem. But first, there was this problem, right? I said that we got it for dimension 4, we didn't get it for dimension 3, so there's one problem. Might be hard. I would guess it's hard, but I really don't know how. And then here we had something, effectively, this is the first theorem you could imagine beyond a constant number of counters, right? Like inverse Ackermann counters, you can't really get much less than that without being constant. So really the question is, does there exist a constant number of counters for which reachability in unitary d-dimensional simple linear particles is in NP hard? I'm not sure that either. Now I'm going to focus on the final theorem, and it's, which is hopefully pretty, but it's very precious. So I had to stretch, the section headings getting really long. I had to stretch the time out to 2 lines. Let me just be clear with what the input of this problem even is. Firstly, we'll just input a number in unary, and I'm going to have a 2-dimensional system, right? It's unary, so the size of this must be polyk. I can write down numbers in the unary sense. And I'm allowed to write down the initial and target configurations in binary. So because the 2-dimensional system U has 2 components, I'm going to say that the 2 values are absolute value S 2 to the K. Same with the target. Is reachability? Can you go from the initial to the target? It's the same question. There is kind of 2 parts of the proof. I'm going to talk about one of them. The other one's like, I'm going to brush under the carpet, but I really shouldn't do it. Like if I brush under the carpet, you would see a mound under the carpet. It's a big thing to brush under the carpet. So the first is I'm going to identify a nice, I am lying to you when I say nice, it is rather not nice, but it is a collection of sufficient, I should have said, a collection of sufficient paths. I think this is really bad for typos. A collection of paths that is sufficient for witnessing reachability. And then once you're given this kind of structural reachability theorem, you can then do some dynamic programming. This is the bit I'm going to sweep under the carpet. I'm going to focus on this. Don't worry, I've written it nice on the next slide. And once we've got this theorem, I will explain roughly what the dynamic programming will do, but it does some clever things I'm not going to do. Okay, so here's a kind of compressed from the paper. Basically, if I give you a unary 2-dimensional simple linear part scheme, I will argue that there is a polynomial bound, something I think I've noticed here, n. And the idea is that whenever reachability holds, so whenever you can get from the initial to the target, there is some path that has one of 2 flavors. I'm going to focus on the second flavor. It's getting real ugly. I gave the second flavor because the first flavor is even worse. Let me try and explain this with my hands now. So in this flavor, I'm not going to see a quote unquote small configuration. There's a configuration inside the polynomial M box. So I'll start at F somewhere and I'm targeting T. And I claim that there will always be a run with the following kind of structure. There is a short path to a certain point just before a cycle. This cycle can point in any direction, this kind of magentary purplish cycle. It could point up here, it could point down there, it could point straight back, I don't know. But it will point in a direction such that you will eventually reach a configuration that is bounded on one counter above by n. So either, in this case, the first counter is at the most n, or in this case, the second counter is at the most n. But I promise that it will be bounded on one of the counters by at most n. From there will be a little path to a cycle that has this kind of flavor of being positive on one, negative on the other. And there's this zigzagging behavior. So you'll get a cycle that sends you to this section. And after you'll take the cycle over and over again, and you're not allowed to kind of finish in this big space where both counters are at least n. You'll kind of traverse between one counter being bounded above by m, the other counter being bounded above by m. And there'll be like little paths between them, and then you'll zigzag like this. With an exception. The exception is that the last two cycles, I can't restrict. We really try to restrict the last two as much as possible. They can do literally anything. They can point in any direction, and they can be taken as many times as they like. They will then just leave and do something ridiculous. They'll go off to Mars, come back to Mars, to the moon, and then finish at T. Something like this. Who knows? But critically, notice that the behavior of the blue cycles is very restricted. From this point here, if I'm promising that you'll take this blue cycle, and I also promise that you'll end up in this sliver, there are only n configurations that you could end up at, right? Because this cycle is slowly pointing you towards the axis and will decrement you, in this case, on the first counter. So at some point, this cycle will send you to have a negative value on the first counter. So if you're forced to end up in here, the cycle, you can only hit the cycle some number of times between, I don't know, like k and k plus n, very roughly speaking. And the dynamic programmer will abuse this fact by guessing which cycles you take to zigzag, and given that you will zigzag, it will try one of the k many outputs, and then it'll continue one of the n many times, and one of the n many times, and n many times, etc. Until you get to a point where you're like, I don't know what's going to happen, I'm going to take 2 more cycles some magic number of times. This will then correspond to an instance of integer linear programming with at most a constant number of variables. So I can turn this into an ILP where I have one variable telling me how many times I'm going to take this magic cycle, and another one telling me how many times I'm going to take this magic cycle. Integer linear programming with a constant number of variables is p time for whatever constant you like. We will only have 2, so it's integer linear programming with 2 variables. That's solvable in polynomial time. So I'll do some dynamic programming and then some ILP solving at the end. But flavor A. So first, I allow in this case that you're allowed to reach the small regions. This is the other flavor where you can see the small region, or rather you will see the small region, otherwise you're in flavor B. Don't worry about this kind of shadow that goes to the run somewhere behind it. This will become clear. There's a box waiting to explain that. So if we start at S and we're targeting some value T, and I promise you you're going to see the small region, it's actually basically the same thing, except at the very start of the run I have 2 magic cycles. I have no idea how many times I'm going to take it to point in any direction. I'll solve a constant dimension ILP and I'll place it somewhere in one of the slivers. I'll then zigzag just as before, and then at some point I promise that you'll see a really small box. And at this point we then use, because these 2 points are very small, you can view these as points encoded in unary. I'll then solve reachability in a unary system. It will remain in here, hence this weird black squiggle that's all small. I'll do reachability in a unary 2-dimensional system between 2 unary points. This is black boxed. This value m is based on the maximum counter value that you'll see when doing reachability in a unary system, or dimension 2. And then we'll end up here, and then you'll go to the target, and then you'll zigzag out. Hence why I've split this into 2, because trust me, I had them overlaid originally, and yeah, I was a proper headache, Jesus. So then you'll leave this BQ point right here, and you'll go and zigzag out. Then there will be 2 more cycles. I have no idea how many times you're going to take them. They point in whatever direction you like. I will do some dynamic programming to zigzag through, and then some small constant dimension integer program, and I'll reach T. So those are the 2 flavors. The first flavor was I never see a point here. There's a slight difference in that I don't know what happens on the first cycle, but it doesn't send you there. It just sends you to one of the slivers, zigzag to do sort of strange cycles. Here, I have 4 strange cycles, 2 at the start, 2 at the end. And then the middle bit had a very similar flavor. Zigzag, 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 some small region, zigzag, zigzag, zigzag. That's the rough structure of the theorem. I hope that makes some sense. And yeah, I think that pretty much concludes. Unfortunately, I hope the few words I said about the dynamic program are believable. There's a lot more left, but I don't think it presents as well, and I've been speaking fast already and giving you too much. So yeah, I guess I will conclude. Here are the 4 theorems that I either explained or at least mentioned, and 2 of the problems that relate to these theorems that I mentioned earlier. Yeah, that concludes my presentation. Thank you very much for attending.